So it's a great pleasure to be here, as always, in Singapore. And I'd like to thank KK and Lars and all the organizers for inviting me to this wonderful celebration. It was 23 years ago that I gave a talk at Yang's 70th birthday in Taipei. And that was a great pleasure, and I was delighted to accept this invitation to return. And I hope to be here in 23 years for another celebration. My talk today is about what I regard as the most beautiful of all Yang-Mills theories, non-abelian gauge theories, QCD. And we are celebrating 60 years of the publication of a remarkable paper which introduced the concept of non-abelian local symmetry, local gauge symmetries, now called Yang-Mills theories, to physics. This is the introduction to that paper, where it is pointed out that the usual principle of isotopic spin symmetry is not consistent with the concept of localized fields. This sentence has drawn some attention over the years because, of course, in some sense it is consistent. It's just not satisfactory. And the author has pointed out a more satisfactory notion of local gauge symmetry, which didn't require the fact that you have to rotate the whole universe at once, something that smells of action at a distance. Now, symmetry, of course, has been one of the main themes of 20th century science, and especially one of the main themes of Professor Yang's research. Symmetries have played such an important role because although the laws of nature that we strive to discover and understand summarize the regularities of events which are independent of initial conditions, symmetries organize the laws of nature themselves. They summarize the regularities of the laws of nature and constrain them and are independent of specific dynamics. Symmetry principles provide a structure and a coherence to our understanding of nature, to the laws of nature, much as the laws of nature provide a structure and a coherence to the set of events we use to explore nature and test our ideas. Now, we recognize at the very least two general sets of symmetries as we have discovered in nature: global symmetries and local symmetries. Global symmetries, which are the oldest to be recognized and used in physics, are regularities of the laws of motion, the laws of nature, but are formulated in terms of physical events. The application of a symmetry transformation yields a different physical situation, but all observables are invariant under that transformation. That's what we mean by a symmetry. So we can rotate our laboratory globally, and the results of all experiments will remain unchanged because the laws of nature are invariant under rotations. That's rotational invariance. So rotating the laws doesn't change the experiment, and we don't have to note in our papers where and when and at which angle our laboratory was situated. Associated with such global symmetries are conservation laws. For example, in the case of rotational invariance, the ensuing conservation law is that of angular momentum. Local symmetries are a little more abstract, perhaps, a little more subtle. Local or gauge symmetries are formulated only in terms of the laws of nature themselves. The application of the symmetry transformation merely changes our description of the same physical situation. It does not lead to a different physical situation. Now, local symmetries, gauge symmetries, first appeared, unbeknownst to the inventors, in Maxwell's electrodynamics. Maxwell's electrodynamics is summarized here. The electromagnetic field strength, the electric and magnetic fields are defined in terms of an auxiliary vector potential. And the dynamical law is Maxwell's laws. The divergence of this tensor is some external conserved current, and the field strength obeys the Bianchi condition. This is Maxwell's equations in modern form. There was great debate in the latter part of the 19th century as to what the meaning of this auxiliary vector potential was at all, since it doesn't really enter into the equations of motion and is not an observable, at least was not thought to be an observable in any sense. And indeed, the equations are invariant under somehow the screen here has shrunk. There's a lambda there, off here. A mu can change by a gradient of a local field, lambda of x. And under that transformation, the equations are clearly invariant, but there are no new charges. Now, Emmy Nether showed that once you have any continuous symmetry of your equations of motion, or the Lagrangian that leads to those equations of motion, there will be associated a conserved current. So given a local symmetry like this, where a mu changes by the divergence of a field which depends on x, there should be a current labeled by that field, an infinite number of conserved charges, and indeed there are. Following Nether's prescription, you can construct currents J mu, which using the equations of motion are just the divergence of this quantity, a different quantity for each function lambda of x, an infinite number of conserved currents, and supposedly an infinite number of conserved charges. But if you actually construct the charges, they are integrals of a total divergence of the electric field times lambda of x, and therefore, for all but lambdas that approach a constant at infinity, they vanish. There are no new charges. In quantum mechanics, there are no new operators generating symmetries of your Hamiltonian or of your states in the Hilbert space. So the local symmetries are symmetries of the Lagrangian, the action, the equations of motion, but they lead to no new transformations of the physical Hilbert space. They lead to no new transformations of physical objects. They are, in a sense, describing a redundancy in our description of the laws of nature. Gauge symmetry, in a sense, again, the screen is much too short, and it is cutting off my final message, which is gauge symmetry equals redundancy. Therefore, for many years, indeed before quantum mechanics, people asked, is gauge symmetry a real symmetry? Is the vector potential a real object? Wigner famously wrote in his, there's some way, does anybody know how to shrinking, enlarging the screen?
You might have to change your format.
I might. Let me see if I can go on. I'll read it to you. This gauge symmetry is, of course, an artificial one. Similar to that we could obtain by introducing into our equations the location of a ghost. The equations must then be invariant with respect to changing the coordinates of the ghost. One does not see, in fact, what good the introduction of the coordinate of the ghost does. So that was Wigner's comments about local gauge symmetries as expressing some real feature of the underlying physics. But it was, of course, Einstein who first realized that there was something, as Yang and Mills later pointed out in the case of isotopic spin, that there is something that smells wrong about insisting on global transformations, in his case of space-time. Special relativity was based on global Lorentz invariance, where you make a transformation from one inertial frame to another, but you transform the whole universe to a different inertial frame. And his theory of general relativity was based on local reparametrization of space-time transformations, and which, of course, we are celebrating this year the 100th anniversary of Einstein's equations, which embodied that local diffeomorphism invariance and gave rise to general relativity. When quantum mechanics came about, actually even around the same time, Weil introduced what he called a gauge symmetry, a local dilatation or scaling transformation of space-time in the hopes of giving a geometrical derivation of electricity and magnetism. This, of course, didn't work. There was a problem of an eye appearing. It didn't exactly work, but London shortly explained that you could give a gauge interpretation of electromagnetism as a complex phase symmetry, which was quite natural in quantum mechanics, which introduced complex wave functions to describe charged particles. And Yang and Mills then extended this gauge symmetry to non-abelian gauge groups, where even to write down the equations of motion in a local form, you needed to introduce the gauge potential, satisfying the non-abelian gauge symmetry. The fact that you need this redundant field and consequent local symmetry to express the laws of physics in a local fashion actually goes all the way back to Maxwell, who realized that in order to understand the local and nature of electromagnetism, it was necessary to introduce a gauge potential. But then in quantum mechanics, in order to describe the Hamiltonian equations of motion of charged particles, you also, in a local fashion, you need a gauge potential. So this redundancy, which is one way of looking at local gauge invariance, is a necessary condition to try to formulate the laws of physics in a local fashion. But what are its implications? It doesn't actually transform the laboratory. It doesn't lead to new conservation laws. It's a redundant way of describing local physics. What Yang told us, importantly, is that it dictates the nature of the interactions. Gauge symmetry produces no new conservation laws. It does something even more important. It tells you how to describe the interactions of particles. And of course, that's why it's the basis of the Standard Model, which, as we learned following those exciting years in the late 40s and by the middle of the 1970s, are all described by gauge forces. Three, in addition to Einstein's local gauge theory of space-time, we have the three subnuclear forces, 1, 2, 3, that govern the structure of atoms and of nuclei and of subnuclei, and just about everything. And this has, of course, been realized with now in a way that has been tested with extraordinary precision, seems to apply just about to everything we observe and measure, with the exception of one force of nature, which has recently been confirmed, the Higgs sector, which, unless you believe in supersymmetry, does not naturally fit into the gauge story, has to be added, although in supersymmetric versions of the standard model, can also be thought of as a consequence of gauge invariance. 1, 2, 3 are label actually the rank of the gauge groups. Electromagnetism was an abelian gauge group, gauge symmetry, and Yang and Mills extended that to a non-abelian case, and they appear in the weak and strong interactions with not just the one electric charge of Maxwell, but 2 in the case of the weak and 3 charges in the case of the strong interactions. Now, Yang-Mills theory appeared in 1954 or 6, 5, 6. I think the paper was published in 1956, if I'm not. No, 54. So why did it take so long for it to find its way into the standard model? There were, of course, from the beginning problems. The problems were evident to the authors of the famous paper and to its first critics. And indeed, as Lars commented, it was quite brave in the face of such obvious problems to proceed with such a bold hypothesis. The problems were manifold. I'm not going to describe them all, but in my opinion, the main problems in trying to apply Yang-Mills theory to the weak interactions were twofold. One, the gauge mesons, the carriers of the force, the analogs of the quanta of light, the photon, were massless, charged massless if the underlying gauge symmetry was a local version of isotopic spin. And obviously such massless long-range forces had not been observed. And it was evident to Yang and Mills and to their critics like Pauli that given the symmetry that was the basis of the theory, the masslessness was protected. There was no way to easily get rid of it. So nature, it clearly was an unphysical idea. The other problem was that the symmetries that one imagined turning from global to local, such as isotopic spin or any of the other flavor symmetries, as we now call them, were not exact symmetries. And again, it makes absolutely no sense to try to gauge symmetries that are broken. And at that time, there was little understanding of the phenomena of spontaneously broken symmetries that are broken by the vacuum, but not in the equations of motion. And and in any case, even if one looked at broken symmetries, which are commonplace in physics, they appear in crystals which break the translational symmetry, magnetism, which breaks the rotational symmetry of the laws of nature, superconductivity, which breaks a local electromagnetic gauge invariance, and as it will turn out, the electroweak interactions. It is not uncommon that the energy landscape of a many-body or relativistic quantum mechanical theory, for example, has as its symmetric state an unstable state of higher energy than the many possible broken symmetry vacua. But even when trying to apply the idea of breaking spontaneously, as happens in crystals or magnets, the symmetries that might the non-abelian symmetries like isotopic spin that might be gauged, one runs into the problem that for every broken global symmetry, there exist these modes that with dispersion relations that are linear, or what we would call in relativistic quantum mechanics massless particles. So any attempts to apply Yang-Mills theory to the weak interactions ran into these problems of massless gluons, or if you tried to break the symmetry, massless Goldstone bosons. And as we all know, both problems were solved in the early 60s by Brout, Angler, and Higgs. And this mechanism not only explains how you can gauge in a consistent fashion a broken symmetry, but when you do so, as was done incidentally, of course, even earlier in BCS theory for the spontaneous breaking of local abelian gauge theories, you both produce a mass for the carriers of the force, the W and Z in the case of the weak interactions, as well as eliminate the Goldstone bosons. And of course, that simple perturbative mechanism has been now confirmed brilliantly at the LHC just about 3 years ago, where the Higgs was discovered as hypothesized in the simplest standard model. Now, in the case of the strong interactions, the problems were perhaps even more severe, since it wasn't evident at all what the charges, what symmetry, the non-abelian gauge symmetry, could act on. Originally, again, it was thought to be flavor symmetry, but all attempts to use flavor symmetry as a basis for a gauge theory of the strong interactions were failed. The carriers of the force would have been rho mesons, which were certainly not massless, and so on and so on. Also, in the case of the strong interactions, one couldn't do much anyway, since they were strong, one didn't know how to handle them. There, the charges, which, as we know today, are colored quarks and gluons, were totally hidden. It's not that the symmetry was broken. Symmetry is not broken. The charges were confined or hidden. And no matter how hard one smashed hadrons together, one never produced a quark. So although it looked to some extent like hadrons were made out of constituents, fractionally charged half-integer quarks, which had even color assigned to them, there was no evidence of quarks in nature. For me, the breakthrough, and I think historically the breakthrough in understanding the strong interactions came with deep inelastic scattering experiments at SLAC, which discovered that the proton did look like it was made out of quarks, not only made out of quarks, but quarks that were freely moving around, almost non-interacting when viewed at very short distances, at very short times. The scaling, so-called observed, was only understandable if the quarks interacted very weakly, and the cross-sections obeyed quark model sum rules. And many of us were convinced by this that this is indication that the proton is made out of quarks, which raises another mystery. How come these quarks, which are bound together in protons, are moving freely as seen by these experiments? This experiment was awarded the Nobel Prize for the discovery of quarks. Now, this freely moving behavior of quarks inside the proton when viewed at short distances is rather strange. And although by then we had learned enough about quantum field theory to understand that forces could look different at different scales of physics due to renormalization, due to the physical effects that give rise to the renormalization of the charge, all theories that had been studied, like quantum electrodynamics, so successful, had the obvious phenomena of screening electric charges. It is natural that if you have a medium, such as the quantum mechanical vacuum, and you put a charge in it, the various dipoles that make up the vacuum will rearrange and screen the charge so that the electric force that an observer observes will be larger as you get closer and closer to the bare charge and weaker at large distances. This is exactly the opposite of what's seen at the SLAC experiment, where the force between the quarks decreases at short distances. In fact, this phenomena of quantum field theories, or of many-body systems in general, but certainly in quantum field theories, is true just about of all theories in 4 dimensions, which is why Lars said that there are so few 4-dimensional quantum field theories. In fact, the only ones that seem to make physical sense are asymptotically free theories, and was the reason for Landau in 1960, that says Landau 1960, to reach the conclusion that QED is inconsistent. If you try to look at the bare charge of QED, it becomes infinite. Those infinities occur actually at a finite distance. It's the Landau-Paul. And he concluded that the Hamiltonian method, or actually local quantum electrodynamics, is inconsistent and must be abandoned. Well, what we discovered was that non-abelian gauge theories, Yang-Mills theories, have the remarkable properties, in fact unique among renormalizable theories in 4 dimensions, of asymptotically approaching free field theory, of having the opposite phenomena, of becoming free field-like, non-interacting at very short distances. And that could explain the scaling seen at SLAC, and that's why we propose that they be used to construct a theory of the strong interactions, which is indeed QCD. Now, anti-screening in QCD, the opposite phenomena, could have been guessed at from a simple physical argument, namely thinking about the medium, which is the quantum vacuum, as in magnetic terms, and noting that their virtual gluons, in the Yang-Mills theory, are charged. Once you make the gauge symmetry, as Yang and Mills did, non-abelian, the carriers of the force, the gluons, or the W and Z, are themselves charged, as they noted. The carriers of the Yang-Mills field were charged vector mosaics. And they behave as paramagnets, as permanent magnets, and the vacuum is full of them. And if you put in a test magnet, it's enhanced by those virtual magnets, leading to an increase of the force at large distances and a decrease at shorter distances, exactly the opposite of QED. That has the consequence that the strong force mediated by the chromodynamic non-abelian gauge field set up between colored quarks, color being the charge, does not obey Coulomb's law, as it would in the absence of the quantum mechanical vacuum, but instead, which would of course lead to a finite ionization energy, but instead, in the complicated QCD vacuum with fluctuating fields, the flux is squeezed to form flux tubes, and that leads to an increasing force as you pull the particles apart and a decreasing force as you push them together, both to asymptotic freedom and to what is called confinement, the fact that you can never pull the quarks out of the nucleus. So the problems disappeared once the color is identified as the charge. Asymptotic freedom explains why the quarks are a good perturbative description of hadrons at short distances, and the strong force that ensues at large distances explains why they're permanently confined inside hadrons. So the key dynamical property of non-abelian gauge theories is this asymptotic freedom, and that dominates the structure of the strong interactions. The verification of that, by the way, took years and years. This is 89, 16 years afterwards. This is how the force is decreasing as you go to shorter distances in this direction. And although there's some indication of decrease, I must say a straight line fits this data just as well. But nowadays, the standard model, QCD, certainly asymptotic freedom, have been tested with exquisite precision. Now, to use such a theory to explain hadrons, to explain the proton, the neutron, the K meson, the strange particle, the lambda, et cetera, is not easy because the force gets stronger and stronger at large distances. You have to control the vacuum. And this is a more accurate calculation, this picture of what the vacuum looks like as fluctuating chromodynamic fields, as seen in lattice QCD, which it remains, so far, the only tool for precise, controllable first principle calculations of hadronic properties, and has been enormously successful, reaching a new level of maturity due to Moore's law and to theoretical ingenuity. And I recommend that you, down here it says, see talk by Michael Kreutz later in the conference. But I did want to just point to a slide which shows a comparison of the light hadron spectrum of QCD as calculated by lattice gauge theory. Again, you don't see here the names of all these particles. The proton, I think, is one of them here. These are particles seen in BEPT, particles involving B mesons. And so they're up here. They're quite heavy. These are the normal particles, the rho, the K, the lambda, the proton. We can now calculate first principles and controllable errors to 1% or better the mass spectrum of all those particles that were being discovered when Yang and when I were graduate students. It's enormously pleasing. But I wanted to justify my title and explain why QCD is a perfect theory. It has no infinities. It has no adjustable parameters. It has no new physics at short distances or large energies. This is somewhat of an exaggeration, but you'll have to forgive me. So first of all, it has no infinities. Infinities, ultraviolet divergences, plagued quantum field theory since its birth in the 1920s. So much so that the inventors of quantum field theory, Wigner, Dirac, etc., gave up on quantum field theory. They expected that it was just wrong. They needed some other revolution in order to make sense out of it. So in that sense, QCD is nice. There are no infinities, period. QCD has no ultraviolet divergences at all. The local Bayer coupling, the chromodynamic charge of the quark, vanishes. That's asymptotic freedom. The only infinities that ever appear when you do, say, perturbation theory and the way we learn with Feynman diagrams, are simply due to the fact that you're expressing physical observables, which always refer to some finite distance, in terms of those that are define the theory at zero distance in a local theory. Now, if you divide a meter, 1 meter, by 0 meters, you obviously get infinity. But that's not anywhere in the physics. And if you take the best way we have, and again, it's the best way we have to explicitly calculate in QCD, namely put the theory on a space-time lattice of lattice spacing A, reduce the answer to the partition function, say, thereby to a multi-dimensional integral, but finite dimensional, and the weight being, of course, the exponential of the Yang-Mills action divided by the coupling constant as defined in the lattice spacing. No infinite quantity appears here. And then you define the theory as the limit. As A goes to 0, the number of integrals gets bigger and bigger, of course, in a finite volume. Letting G of A approach 0 as calculable by asymptotic freedom, you get a finite answer. That's what people doing lattice QCD use to calculate the masses of hadrons. Infinite quantities never appear. There are simply no infinities. Second of all, there are no adjustable parameters. Now, that's a bit of an exaggeration because quarks, of course, have masses which have nothing to do with QCD, so we can't calculate them. But they don't play a big role in hadronic physics. The light quarks are very light. The heavy quarks are very heavy. To a good approximation, we can set the up and down and strange quarks to 0 mass, the heavy quarks to infinite mass. They decouple. We get a very good approximation to the real world. Everything else then is calculable. The theory has, as Yang and Mills pointed out in their original paper, no dimensional parameter. The coupling that defines the strength of the theory defines what the scale of lengths are because it varies with length. So we need some parameter, physical mass to define physics, but having done that, the coupling is fixed by that scale. And so all mass ratios are calculable. And if you ask what the origin of the proton mass is, and in public lectures to young students, I love to point out that their mass, which they have no idea where it comes from, I explain to them that it's all confined energy. And it's calculable in terms of the one mass scale you need to introduce, the place, say, where the Yang-Mills coupling is 1. All mass ratios are then pure numbers, which in principle, up to quark mass corrections, could be calculated with arbitrary precision. So that's the first time we've had a theory with no adjustable parameters. And finally, every theory we've ever had in physics has buried inside of it its limitation, someplace where it breaks down, usually at shorter and shorter distances. In QCD, there's no new physics at short distances or arbitrarily high energies. In fact, to the contrary, at high and higher in energies, QCD becomes simpler, perturbation theory, more exact. We can, in fact, control a divergent asymptotic expansion, which is what perturbation theory and quantum field theory is, by going to shorter and shorter distances. This has important conceptual and implications. It allows us to extrapolate theoretically the Standard Model to arbitrary high energies. And it, in a sense, solves one of Dirac's famous large number problems. Here it says the mass of the proton divided by the Planck mass is about 10 to the minus 19, a very small number Dirac worried about. But we can extrapolate the strong force gets weaker to a point where it joins with the other forces. And this is one of the reasons that and the fact that gravity becomes strong at about the same Planckian distance is one of the strongest clues to how to unify the Standard Model forces with gravity and might explain why this number is so small. It is simply that at the unification scale, the nuclear coupling is whatever it is, like 1 over 25, something like the electromagnetic coupling at that scale. And then as you go to larger distances, you get to a distance where the force between the quarks is strong enough to hold them together. That defines the size of the proton and thereby the mass of the proton, which is all this kinetic energy in that confined space. So you can calculate the mass of the proton compared to the mass of the cutoff, or the Planck mass, and it's the exponential of 1 over the coupling at this scale, which for Standard Model-like couplings is exactly the right order of magnitude. So QCD is perfect because it's the first example of a complete theory, if you ignore everything else in the world, with no adjustable parameters, no indication within the theory of a distance scale where it might break down. There's infinite bandwidth. But, of course, in the real world, we'd like to understand why SU3 gauge symmetry. What about the quarks? Why are they there? Their masses. And that we know, of course, experimentally, that there are other forces in nature, including gravity. So in the many years since QCD completed the Standard Model, there have been extraordinary impressive tests of quantum chromodynamics, impressive calculations in quantum chromodynamics. Here are some of the ones I like, which have to do with the running of the coupling, which has now been carried out to many, many loop order. But again, here I have on my slide C talk by George Sturman, who will talk about the application of perturbative QCD to LHC physics, right, George? Something like that. Which is absolutely essential. So in the LHC, we now are look for new physics, and typically one new interesting event per billion boring events. But to pick out 1 out of 1 billion events, you have to understand those 1 billion events with enormous accuracy. And the technology of calculating within QCD, the perturbative expansion, is just totally amazing, as well as the agreement with experiment, which I showed here. This is, I think, a dijet calculation and experiment from CMS. And note that this is 10 to the 11, and this goes down here to 10 to the minus 1. This is a factor of a trillion, million, 12 orders of magnitude agreement of theory and experiment. Then, of course, there's the fact that quantum chromodynamics, the theory of quarks and gluons, can exist in different phases that we never dreamed of, and which are being explored at RIC and at ALICE at LHC, not just the hadron gas of confined quarks and gluons that we see at low temperature and low chemical potential or low density, but a quark-gluon plasma whose properties are being explored at RIC and at LHC, and perhaps fascinating new phases that might play a role in neutron stars or quark stars or high-density nuclear matter. But perhaps the most interesting new aspect that has been revealed of non-abelian gauge theories, and especially QCD in the last 30 years, has been its connection to string theory. So when you pull quarks apart, they form because of the properties of the vacuum, the flux is squeezed into tubes, and mesons look somewhat like fat strings. And this is why string theory emerged from an attempt to understand the nuclear force and the properties of hadrons. The focus originally indeed was on open strings, relativistic open strings with labels, Chan-Payton labels, I think. Chan is here, which would describe open strings, or in gauge theory, gauge mesons, where these would be the charges or labels of a gauge meson in the adjoint representation of SUN. Indeed, this connection between gauge theory and string theory is now gone from wild hypothesis that led to string theory now to something that everyone knows, some special cases, is true and is generally believed to be the case. What is truly exciting, however, is that string theory discovered in its evolution that when you have open strings, you can close them, and that closed strings describe gravity. And therefore, string theory led to a unification at its conceptual level between gauge theories, theories of open strings with fundamental quarks or labels at their ends, to closed strings that have no labels and describe fluctuations of the vacuum or indeed of space and time. By now, that understanding has grown and proven so fruitful that I think of the framework of theoretical physics in the following way: not as quantum field theory, the basis of the standard model, and this bizarre theory of extended objects called string theory. Neither of these are theories, by the way, they're frameworks, as being one and the same thing. And we have many indications that this is the case, some special cases where it is beyond question. And this is the general framework in which exploratory research in theoretical fundamental physics goes on nowadays, almost exclusively, with a hope eventually of understanding how this thing, which is called the standard model, or the standard theory, eventually fits in or is picked out. At the beginning, this began with what's called large N QCD. What happens to Yang-Mills theory when you take the N, or the rank of the gauge group, to infinity? And the remarkable thing is that there's an incredible simplification in that limit. If you regard the number of colors not as 3, but as infinite or large, you can show that the theory must be non-interacting with an infinite number of stable glue balls. So pure Yang-Mills theory is made out of glue balls in a confining theory. The gluons are confined. When n goes to infinity, there's an infinite spectrum of massive glue balls, but non-interacting, all stable. In fact, you have an effective theory in which, as Nc goes to infinity, you get the classical limit. And all quantum corrections are governed by powers of 1 over n. So large n, n being the n of SUN, say, for Yang-Mills theory, large n is like something of a classical limit of QCD, as well as a string theory. That classical limit could be described by a classical string theory. Classical theory has an infinite number of spectrum, all the oscillations of the string. And classically, it's non-interacting. There are no loops. There's a lot of evidence for that in quite generality from the planar structure of Feynman diagrams in non-abelian gauge theories in large N. The fact that 1 over Nc, 1 over 3, in fact, tends to be a good approximation for hadronic phenomenology, but most importantly, within string theory, to this duality or mapping of string theory to gauge theory. In fact, since Lars is going to talk about the maximally supersymmetric gauge theory, I want to say a word about it. I regard it as the hydrogen atom of quantum field theory. What I mean by the hydrogen atom is an integrable model, which is a good approximation to the real world. And such integrable models that are good approximations to the real world have had an enormous impact on physics over the years. In fact, they've guided the historical development of modern physics. For example, the simplest example of an integrable model that's a good approximation to the real world is the Earth's orbit around the sun, which is governed, a good approximation just as a two-body force law, which is 1 over r squared. Now, 1 over r squared in 4 dimensions is nice because it's actually integrable. And this, neglecting the other planets, is a good approximation to the real world. And it is lucky that it is the case, because it would have taken Newton or somebody else much longer to discover classical mechanics and Newton's law of gravitation if we weren't, to a very good approximation, living on an integrable orbit. This same picture played an absolutely important role in the early development of quantum mechanics, where the Bohr model, which essentially assumes simple orbits with a 1 over r squared force law, is such a good approximation to hydrogen atom because hydrogen atom is integrable, and the Bohr law was a semi-classical quantization of a quantum theory which didn't exist. So if one hadn't had before one's eyes this simple integrable model, it would have been very difficult for Bohr to have guessed the semi-classical approximation to something that didn't exist yet. It led to non-relativistic quantum mechanics. The Dirac equation is also integrable, and that helped enormously in the development of relativistic quantum mechanics. So historically, through relativistic quantum mechanics, starting with integrable models that are a very good approximation to the real world, and then exploring the corrections, is what led to classical mechanics, non-relativistic quantum mechanics, relativistic quantum field theory. Well, asymptotically free QCD, or non-abelian gauge theory, to some extent already is like that, and that's why it's been so successful and possible to develop, because, again, for very large momenta, because of asymptotic freedom, we have a trivially integrable system of free, non-interacting quarks and gluons about which we can perturb, and which becomes a better and better approximation to the real world as you go to higher and higher energies. But the most interesting one of this is maximally symmetric. So n equals 4 is the maximal number of supersymmetric extensions of Yang-Mills theory. And again, when the number of colors becomes infinite, that theory becomes, we believe, integrable. We're very close to actually writing down the exact analytic, on paper, solution of this limit of non-abelian gauge theories, or of QCD. Now, if we wanted to make contact with QCD, we would, of course, have to break supersymmetry, not difficult, put in quarks, not difficult, but calculations then become difficult as you perturb away from the integrable limit. But this, in a way, is the closest thing to the hydrogen atom in relativistic quantum field theory that we've ever had, and it is amazingly informative. And this understanding has partly been based on and feeds into this remarkable duality between gauge theory on the one hand and string theory, living in this is ADS-CFT. This theory, this integral model, is dual to a string theory in 10 dimensions. The limit of n going to infinity is the limit in the string theory of Planck's constant going to 0. Becomes the classical limit of that superstring theory. And here it says, see talk by Lars Brink. So a word to get, well, I think I'm going to skip this slide and trying to explain what ADS-CFT is, but just tell you how enormously productive this hydrogen atom is and this duality between string theory and gauge theory. It has given us new insights, of course, into gauge theory. It produces a string theory of this cousin of QCD. It allows us to tackle problems in QCD, like, say, the transport coefficients of the quark-gluon fluid produced at RIC before it decays into hadrons, something which is beyond our capability directly in QCD, but easy to calculate in string theory by solving Einstein's equations with surprising success. The same applies to condensed matter physics. The hallmark of this hydrogen atom of gauge theory, this supersymmetric gauge theory, is that it is conformally invariant. It's conformally invariant, it's integrable, it's everything at once. But the duality is more general. We now believe that any critical point, any conformally invariant quantum field theory is has a geometric dual, which is a stringy theory. And in the certain limits can be described by the low energy limit of string theory, which is Einstein's theory. So you have now condensed matter physicists solving Einstein's equations in order to learn about quantum critical points that occur at 0 temperature as you vary some physical parameter. Again, with remarkable insights. These are insights between simplified models, between hydrogen atoms. Okay? But they are what is one of the reasons, as Michael Fisher, I'm sure, will tell you, that one studies simple systems to learn about the qualitative nature of very difficult physical phenomena like quantum critical points. From the point of view of fundamental physics, most importantly, this gives us new tools now, starting with a gauge theory, which is by now a standard quantum field theory we can put on a computer and calculate. 2 questions about quantum gravity, which our string theory is a theory of, and is being used to try to resolve some of the puzzles of quantum gravity, like the fate of black holes and the nature of quantum cosmology. And down here I have new concepts of space and time. So I'm going to end by coming back to my original point about local gauge symmetry, redundancy. What is the deep meaning of this gauge symmetry that Yang and Mills generalized from abelian to non-abelian? Is it just a redundant description of physical phenomena? Well, in this new world of string theory, field theory, correspondence, this becomes even a more interesting question. In string theory, you don't see the gauge degrees of freedom at all. To make the correspondence, you can associate those gauge degrees of freedom as dynamical modes of branes, which might be sheets or three-dimensional volumes, points where open strings end. That's where the gauge charges lay. So in string theory, to construct gauge particles, you put in collective vibrations of string theory, of space-time, if you want, which are, say, sheets. Open strings can end on those sheets, and those strings that connect them are the gauge connections, and the places where they end are where the gauge charges are. So in a sense, from the string theory, you can construct these redundant gauge degrees of freedom, if you want, but they're clearly redundant and not visible directly in the string theory. Conversely, in gauge theory, you can regard space-time itself of the corresponding string description and dynamical space-time, otherwise called gravity, as descriptions of the dynamics of the gauge field. And dozens of theorists are now engaged in making a precise understanding of how space-time emerges or could be constructed out of the dynamics of a gauge theory on a rigid four-dimensional space. So this makes the question of what is this redundant description of physics, or gauge symmetries, gauge degrees of freedom, more interesting. Are gauge degrees of freedom emergent from modes of dynamical space-time? Or is space-time emergent from gauge dynamics? Or both? So I'm going to leave you with that question. It is at the center of what we are doing nowadays at the frontiers of fundamental physics. How it will help us answer the question of how does our standard model fit into this much wider and richer framework we've studied, I don't know. But one thing I'm absolutely sure of, that Yang-Mills gauge theory will be at the forefront of fundamental physics for centuries to come. Thank you.
Thank you. Let me, before we start asking questions, let me just tell you a little story about what happened in 2004 when we called David to tell him that he had got a certain prize. This was 2 o'clock in California. That late? But anyhow, well, he can tell himself what happened. But then we had the press conference afterwards. And we had David on the phone. So I was sitting there and had a microphone next to me. And that was David. And so then one of the, so there were, hundreds of journalists from all over the world. So the journalist asked them, so when did you start to believe that your theory really was the correct one? And David was very polite, and he was, yes, he said, well, during the 80s when, we saw the results come in and they fitted so well, then I started to believe in. But then I clapped the microphone and I said, that's wrong. I said, you knew it 1 microsecond after you had discovered it. Which I still think is true.
Well, there's knowing and knowing.
Yeah.
You know, there's the kind of so you could ask Frank, when did you know that Yang-Mills theory was part of the real world? Now, you might very well answer the same thing for him immediately. It's so beautiful. It must be part of the real world. But then there's the second knowing, which is requires the agreement of the ultimate judge, which is nature, and that comes, as always, much, much later.
Okay. So we are running late. It has happened before when David talks, but do we have any questions? I think if you don't have it now, we take a coffee break. And,
What do you mean when you talk about lattice gauge theory and you mentioned about Moore's law?
Well, all I meant was Moore's law, as you know, is the fact that computers become twice as powerful every, 18 months? Mm-hmm. That has helped lattice gauge theory enormously. Lattice gauge theory began in the middle 70s. It was sort of as a tool for calculating hadrons was originated by Ken Wilson. Ken gave up. Mike was one of the first to continue, but they were working by what is regarded today as extraordinarily primitive computing. And so at that, you really needed modern computers to tackle this very difficult calculation.
Okay. I said to all you young people, feel free to ask David, and he will be so glad to answer your questions outside here. So I think we take a break, and we first have to take a group picture, and then we have to take coffee, and then we have to be back here by 11. So this is we do it quickly.